All right, so let's go ahead and get started. We're going to start our new unit here today. We're going to pick up with Chapter 17. Okay, this chapter focuses around a new functional group, one that I know everybody's long been waiting for, alcohols. Okay. So just to sort of be clear here, an alcohol group, I think at this point we know, is a molecule with that OH bond combination. Okay. Just some quick terminologies. Our functional group here would be the alcohol. But this bond combination right here, this OH, we call a hydroxyl group. All right, so alcohols contain hydroxyl groups. Kind of like how ketones and aldehydes contain carbonyl bonds, right? This hydroxyl group is referring to this particular combination of atoms. The molecule as a whole we would classify as an alcohol. That's its functional group. All right, so let's first talk about some of the physical properties of alcohols. All right, so in terms of our polarity, alcohols are considered a polar functional group. Okay, so let's just look at our simplest alcohol here. Methanol, just one carbon. Okay, so why are alcohols considered to be a polar functional group? Well, they have this very polar bond in there, this OH bond, right? Oxygen, being one of the more electronegative atoms, pulls electron density away from this hydrogen atom here, leaving it relatively electron deficient. Okay, so polar molecules can engage in these dipole-dipole interactions with other polar molecules. So for example, this one can dipole-dipole interact with another alcohol. Right, the negative end, the partial negative end of my one alcohol is going to be interacting strongly with the partial positive end of its neighbor. All right, this is common to all polar molecules, interactions between polar molecules. But we give it a special name when it's got one of these few something and hydrogen bonds here. All right, this is not just a dipole-dipole interaction. It's that next level up in strength. This would be a hydrogen bonding interaction. Okay, so alcohols are considered polar functional groups because they're polar molecules. They got the polar bond, all right, but they're even more so than, say, a carbonyl group because they can hydrogen bond. All right, so what we want to do is we're going to take a few molecules and we want to rank in terms of increasing boiling point. So let's just take a few examples here. We're going to take our methanol. We'll take another 1-carbon compound acetone, or not acetone, formaldehyde. And then just regular methane. All right, and we talk about boiling point as a measure a lot, and importantly, the reason why we use it is it is a stand-in for measuring the strength of intermolecular interactions. All right, well, why is that? So let's think about this for a second. The boiling point is the temperature at which a substance goes from being in the liquid phase to being in the gas phase, right? It's how much thermal energy we have to put in to make something go from the liquid phase to the gas phase. Okay, that's just the definition of boiling point. In the liquid phase, molecules are all next to each other, interacting strongly with one another. When they go into the gas phase, you separate those molecules out. So how do you go from liquid to gas? You got to break those interactions between neighboring molecules. So molecules that have a high boiling point, compounds that have a high boiling point, means you have to put a lot of energy in to break the interactions between neighboring molecules. Molecules that have a low boiling point, they have very weak interactions between neighboring molecules, so you don't have to put a lot of energy in to break them. All right, so we're going to rank these from lowest to highest boiling point, and really that's a stand-in for how strongly these molecules are interacting with their neighbors. So which one of these is going to have the lowest boiling point? This thing's methanol, this thing's formaldehyde, and this thing is methane. Which one's got the lowest boiling point? Methane. Move this over here to the end. Which one has the highest boiling point? The methanol. Okay. These are all the same size, about the same size. All right, methane is non-polar. So it's got very weak interactions with its neighboring molecules, what we call dispersion forces. Formaldehyde is a polar molecule, but it doesn't have one of those special oxygen-hydrogen bonds, okay? There are 3 bonds capable of hydrogen bonding: fluorine and hydrogen, oxygen and hydrogen, and nitrogen and hydrogen. And if you look at where those all are on our periodic table, those are all the smaller and more electronegative elements. This is not one of those bonds right here. So even though this molecule is polar, all it can do is dipole-dipole interact. And our last one is polar, but not only is it polar, it can hydrogen bond. So that's going to give it the highest boiling point, the strongest intermolecular interactions. All right, methane is very low, like negative 161 degrees Celsius. Formaldehyde's about negative 20 degrees Celsius, whereas methanol is closer to 60 degrees Celsius. So you can see there's quite a bit of difference depending on the strength of those intermolecular interactions. Okay? So then we said that our alcohols, they have these OH groups, so they're very polar functional groups. All right, so now let's talk about a different property, not just the boiling point, but now we want to look at their solubility in a very polar solvent, water. All right, and we're going to compare a few alcohols here. Methanol with just one carbon. Butanol, which has 4 carbons. And then octanol, which has 8. Okay? So what I'm going to tell you is that methanol is 100% perfectly miscible with water, right? So 100% soluble in H2O. Butanol is what is considered partially soluble, meaning you can get a little bit of methanol to dissolve in water, but if you add too much, you will form 2 distinct layers. You can only get so much to mix in with that water before it won't mix anymore. And our octanol is completely insoluble in water. All right, so the question is why? Why do we see these differences? We called alcohols a polar functional group. We see that some of them dissolve in polar solvents like water, but other ones don't. So what's the deal here? What's the difference? The big carbon chain on the back end, right? They all share these same polar OH group that is capable of hydrogen bonding with water. Right? But octanol has this gigantic hydrocarbon chain on the back end. And so even though a portion of that molecule is polar, it's also got a much larger portion that is nonpolar. All right? So we got this push-pull going on in our alcohols depending on the size. All right? Our larger alcohols are not going to be soluble in polar solvents like water, at least not something as superpolar as water, right? But if we cut down on our number of carbons, if we decrease the size of that nonpolar region, then we can get it to mix well in water, all right? So all that is to say that you can kind of tune just how polar your alcohol is by the size of that hydrocarbon chain. This molecule right here, it might not mix well with water, but it would do a pretty good job of dissolving something like caffeine, an organic molecule that has some polar functional groups, but also some non-polar areas as well, right? So it's a nice intermediate polarity. And we can change just how polar that compound is depending on how many carbons we add on the back end, right? The larger that non-polar region, the more nonpolar the molecule is going to be overall. And remember, polarity, you've sort of graduated from your general chemistry way of thinking about polarity, of being this black and white, polar versus nonpolar. No, 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 it's much more of a spectrum, right? So our alcohols span the spectrum from all the way on the superpolar side to like kind of in the middle, in that intermediate polarity. So they can be very useful in the lab for that reason, for being used as solvents. Okay? It's also helpful that they're all liquids, right? I mean, methanol is a liquid at room temperature. That's very, very helpful. Not all teeny tiny compounds like that are liquids at room temperature. Formaldehyde, not a liquid at room temperature, right? You're not going to use it as a solvent. Cool, so obviously we're going to spend a bunch of time talking about reactions of alcohols, but first step we got to do is nomenclature. And let's just grab that 4-carbon example that we laid out on the previous page. All right, so step 1, let's find our parent chain. Kind of already gave it away. These 1, 2, 3, 4 carbons right here, right? So our longest continuous set of carbons. Importantly, alcohols are considered a functional group in our nomenclature. So it's going to be our largest continuous set of carbons that contains that OH group. All right, and we got a new functional group here, our alcohols. So we got a new suffix. I think just kind of by virtue of having encountered these things in the lab, you might know that alcohols have that OL ending. So this molecule right here, well, I guess let's finish it up. We got to do our substituents. And then we do have to number our parent chain. Before we put it all together. So this molecule right here, if I number, that OH group is on carbon 1. So this would be 1-butanol. Okay, so real quick, why do I have to include the 1 in the name? This is kind of a situation where sometimes we have to include a 1 and other times we don't, right? So when do I have to include it? Well, you have to include it is if you pick it up and move that OH group and you have a different molecule. You have to include it because there is such a thing as 2-butanol, and it is different than this molecule that we drew right here, right? So we can't just leave it out. 1-butanol is different from 2-butanol. We have to specify the location of that OH group, all right? One more thing to point out here. We have our location, the 1. We have the but for our parent chain, and we have the OL to indicate that alcohol functional group, right? Notice that we also have the AN in the name. It's not butol, but butanol. And what does that AN tell us about our structure? All single bonds, right? There's no double bonds in there, all right? We'll get to that in a second. But notice how we've retained that AN. This tells us that we have all single, I guess specifically single carbon-carbon bonds. All right, so the prefix but tells us how many carbons there are. The OL ending tells us the OH group is in there, but we also have that AN, butanol, to give us our, telling us that there are only carbon-carbon single bonds. Okay, cool. So before we move on, let's just do another one. All right, I'm going to put down a few examples. take a minute and name these three molecules. I'm going to put up one more on here with two alcohol functional groups. Based on what we discussed with our conjugated diene nomenclature, see if you can't work through what that would be. So in this first example, I have my 1, 2, 3, 4, 5, 6 carbon parent chain. If I number in both directions, I got my smallest number going from right to left with my alcohol group on carbon 3. So this would be 3 hexanol. All right, a second example. We have 1, 2, 3, 4, 5, 6, 7 carbons in our parent chain. And we have this methyl group here, a substituent. So I'm going to number from left to right, 1, 2, 3, 4, 5, 6, 7. And from right to left, 1, 2, 3, 4, 5, 6, 7. And which one of these numbering schemes am I going to pick, the blue or the red? Okay, awesome, right? So remember, when we're doing our numbering schemes and we have a functional group in our molecule, for numbering our parent chain, we're going to prioritize that functional group. Okay, so I don't care where that methyl group is. The only thing I'm going to pay attention to is making sure that hydroxyl group has the lowest possible number. So when I assemble my name, this would be 5-methyl-2-heptanol. Okay, we go to our little square here. That is my parent chain, the square, the cyclobutanol. My alcohol group is going to be on carbon 1 in my cyclobutanol. Do I have to put that 1 in the name? No. So here's an example of where I pick it. There's no such thing as 2-cyclobutanol, right? Because as soon as I pick up that hydroxyl group and move it, I'm just going to change what I call carbon 1. So this would be cyclobutanol. All right, and then lastly, we have these 2 alcohol groups, so we would call a diol. Let's just remind ourselves that we covered how we name molecules that have 2 alkenes in it, 2 double bonds rather. This would be 1,3-butadiene. And remember, we kept this A in our name specifically so that we didn't run those 2 consonants together, that T and that D together. So not butadiene, right? Butadiene. Same thing here. Our parent chain are these 1, 2, 3 carbons. Our alcohol groups are located on carbons 1 and 2. So this would be 1, 2, prop. Propan. I'm sorry. Okay, sorry. One more. Try that again. Prop to indicate our 3 carbons. We have the AN to indicate that these are all single bonds, but we can't say propanediol because then we'll be running those 2 consonants together. So like before, we're going to retain a vowel. In this case, we're going to retain that E. This would be propanediol. Okay, and we're just going to make a note. We're going to keep that E. So the N and D are not next to each other. Okay, so we have this, again, our 3 carbons is the prop. We still have that AN in there to indicate that we have all single bonds, but now we've kept that E so that when we make that diol ending, we don't run 2 consonants together. Okay, so lastly, alcohols are going to be the first time that we're going to talk about molecules that have more than 1 functional group in them. So for example, how do we name something like this? Okay, a molecule that has both a carbon-carbon double bond and an OH group. 2 functional groups in the same molecule. We're going to call these multi-functional group molecules. All right, so how would we go about naming a compound like this? We got more than 1 functional group in here, and we've talked about how in our numbering and in our naming and stuff, these functional groups get priority. So how do you deal with it when there's more than 1 functional group? It turns out that all of the functional groups in the world, all of the functional groups in organic chemistry have been given a ranking. Okay, so what we have is a priority ranking of our functional groups. All right, you can look up on Wikipedia, organic chemistry, priority list, right? You get all the different functional groups in organic chemistry, and they've all been ranked. They've all been ranked from highest priority to lowest priority. And we're going to look at just a tiny list here of the ones that we've covered. At this point, our highest priority functional group is that alcohol group. Alkenes are considered a lower priority than alcohols. All right, and our lowest priority functional group that we have are our alkynes. Okay, so this is going to impact two aspects of the way in which we name our compounds. First of all, when we number this parent chain, as we said, we're going to prioritize our functional group. All right? If we got multifunctional groups, which one do we think we're going to prioritize? The highest or the lowest priority group? The highest, all right? So for our multifunctional groups, we're also going to prioritize, but we're going to specifically prioritize that highest priority functional group. Okay, 1, 2, 3, 4, 5, 6 carbons. If I can number from left to right, or from right to left. And which one of these numbering schemes am I going to pick, red or blue? Red. I'm going to only look at that highest priority functional group in order to build my name here. Okay, so when we build our name, we got kind of another issue, which is now we got these two functional groups. We have to indicate the presence of both of these functional groups. But both of these functional groups are referred to as suffixes, right? Alcohols are that OL ending, and alkenes are that ENE ending. So now we have to assemble in such a way where we're going to stack these suffixes in our name. All right, so for really nothing new for regular ones, but again, for these multifunctional groups, all right, specifically our, well, we'll just leave it multifunctional groups. We need to stack the suffixes. So what do I mean by that? Okay, so for this first example that we did, 1-butanol, I could have written this another way that was perfectly acceptable by the IUPAC, where I put the number, the location of that alcohol group in the back half of the name. So I could have also called this butan-1-ol. All right, you can always put the number before your functional group at the end. Now we have to do it. When we're stacking our functional groups, because they're both going to be in the back end of this name, we have to use this format right here. Okay, so this molecule right here, when I go to name it, I'm going to use my prefix, hex. All right, now I get to that how many, single, double, triple bonds here. This would be hex 5-ene, 3-ol. This tells me the location of that double bond. And this tells me the location of that hydroxyl group. Okay. All right, so let's just practice this real quick. All right, so for my first example here, I found my parent chain. I numbered my parent chain as well as identified that methyl substituent. So now when I go to put it together, my substituent's still going to come first, my 3-methyl. But now I've got both a double bond and a hydroxyl group to refer to, so I have to put them both in the back half of my name. So 3-methyl bute, first the double bond, 3-ene, 2-ol. Oh, not 3-ene, I'm sorry. Woo. Just making sure we're all paying attention. What should it be instead? 2-ene, 2-ol. Cool. All right, my parent chain, 1, 2, 3, 4, 5, 6, 7, 8 carbons. Okay, and which one of these numbering schemes do I want to pick, red or blue? Red, right? Again, I'm going to pay attention to only that highest priority functional group. Okay, so my 8 carbons, this would be an oct, and then there's that ene, that double bond on carbon between carbon 6 and 7. So oct 6-ene, 3-ol. I'm not done. What else do I need to finish this name off? Thinking back to our alkenes, the stereochemistry, right? If instead I would have flipped this bond over here in this direction, I would have a completely different molecule, right? Different physical properties, all that jazz. So yes, I have to include the stereochemistry of this double bond. This would be an E stereochemistry. So E oct-16-3-ol. Rolls off the tongue. All right. Cool. All right, so let me just kind of give you a preview of where we're going to be going with this here. The first thing that we're going to be talking about are the different ways that we prepare alcohols. All right, and the first thing we're going to do is cover something that is actually review from last semester, which is the hydration of alkenes. Alkenes are a great starting point in a synthesis reaction. We can make a lot of different things from alkenes. That's why it's one of the first functional groups that are covered in the course. All right, one of the things that we learned how to do is to create alcohols from alkenes in reactions that are called hydration reactions. Okay, so remember, alcohols like to undergo addition reactions, and if we're talking about hydration, what's being added is water. Okay, so if we just take a look at a very simple hydration reaction, okay, and again, we're going to do an addition of HOH. Right, our addition reactions, they take that carbon-carbon pi bond and they replace it with two new single bonds on either side. All right, I still got my two hydrogens on each carbon. I didn't lose anything. All right, but importantly, to one side, I'm going to add that hydrogen from the water. And to the other side, I'm going to add that OH group from water. And so this is how we can create an alcohol by hydrating an alkene. All right, my byproduct over here, I started with an alkene, and now I have an alcohol. Cool. All right, we're going to pick up with that reaction next class, but this is a review of the first semester, so I'm going to go kind of quick through it. We had a few different ways to do it, by the way. There were actually 3 different reagents that we could use that sort of do different things. One of them prefers the more substituted carbon, the other one the less substituted carbon. All right, so we'll review those 3 methods starting next class, as well as introduce one new one.